Okay, so thanks, Marcus, for the introduction. It's nice to be back in Vienna, where this project here was. Most of the work for this project was done. So it should have been on the title slide, but this is joint work with Michael Speckbacher and Daniel Abreu. And my collaborators, I'm sorry, I'm going to dumb this down a bit so that I understand it. But we'll get to the large sieve in a while, but first I thought I'd set the stage for why we're sort of interested in this. So as we saw this morning, we define the short-term Fourier transform, and we have some properties of this, right? And key to this talk here is that we have this Gabor space, which is a reproducing kernel Hilbert space with the reproducing kernel is given by up to a phase factor is given by the translated version of STFT of G with itself. So one thing which wasn't mentioned this morning, which we'll need here, is since we're interested really in local LP estimates of the short-time Fourier transform. So in order to ensure that our problem is that the local estimates are finite, we need the modulation spaces. So we use the Gaussian as a window, and then we define the modulation space MP to be all the temporal distributions whose short-term Fourier transform is in LP. With this, we can define the NP concentration problem. So we take a measurable set in phase space, and we fix a window in M1. Then the question loosely is, what can we say about this quotient where we take the integral only over delta of the p power of the STFT, and we divide over the sort of total energy, which is the p power over the whole phase space. And I've written it loosely here because it's sort of a question which you can study in a bunch of different ways. You can ask about what optimizers are. You can ask about what the maximum is. We're going to do something a bit looser, which is we're going to give some estimate on how big this can be. So motivation for this can come from the uncertainty principle. So in the L2 case, then we know that, for example, if omega is or if delta is a finite or a set of finite measure, then we know the STFT can't be concentrated on that set. So in particular, the quotient we're interested in would have to be strictly less than 1. So let me just quickly say that there are cases where this problem sort of simplifies. In the p equals 2 case, as I guess we also saw this morning, you can restate the whole problem as a sort of eigenvalue, as a problem of finding eigenvalues of a certain operator. And in this case, it would be the time frequency localization operator. In general, though, the problem is harder. And for general P, I guess the best results are really gotten by making stronger assumptions on the window G. Usually the window G in the general P case is assumed to be the Gaussian. So that's really the best way you can get explicitly solve the problem finding the optimizers and or at least the supremum. So the large sieve principle says it has weaker assumptions, and as a result, you get a weaker. You only get an estimate, not a solution, but at least it works for every P. So the classical large sieve principle, at least in time frequency analysis, says that if we pick a G which is in M1 and normalized in L2, then this quotient has to be smaller than this left-hand side, which is some norm on the reproducing kernel of the corresponding Gabor space. So yeah, this is a nice estimate, but I guess the way we should sort of think about this in like the principled sense is that if the reproducing kernel is epsilon concentrated on some omega, then well, we can bound this integral of the reproducing kernel, and we can pretty much replace it by this maximum Nyquist density. So the principle is sort of that if the kernel has good enough decay, then this gives you a sort of density assumption which allows you to ensure that this compression quotient is small on the domain delta. So yeah, there's just from this result, which this was by Abreu and Speckbacher back in 2021. From this result, you can get some immediate consequences. Is that you can basically use it to refine the classical the weak uncertainty principle for the short-term Fourier transform. In this case, I've stated it just for the Gaussian being the window, but in general, if the STFT is pretty well concentrated, so with mu and with F properly normalized, this should be if the energy of the short-term Fourier transform is mostly concentrated on this domain delta, then this domain delta cannot be very small. And I guess you could think of this as refinement because you get this intermediate term where again this integral over the reproducing kernel of the Gabor space shows up. Furthermore, we know that from this there's you can use the large series principle to get sort of Donoghue stark. You can get sufficient conditions for signal recovery. So if we consider the case where we're interested in recovering the operator F from measurements of the short-term Fourier transform, but our measurements are noisy. Here we're assuming that the noise can have finite L1 norm, but the noise must be supported to some domain n. If the noise satisfies the following condition, namely this again we take this large integral over the intersection between the support and some disk center at Z. This is smaller than some quantity. Then we can actually recover F perfectly from the measurements of the short-term Fourier transform by solving a minimization problem in M1. Yeah, so this is all well and good. Where does the quantum part come in? Well, we're always interested in this integral over the pth power of the short-term Fourier transform. As we saw this morning, we can write this as a operator convolution, namely between the rank 1 operator F tensor F and the rank 1 operator G tensor G. So the sort of quantum idea here is what happens if we replace either of these operators with a more complicated operator. So we're going to do this, but in general, what can we sort of hope to find? Well, first thing we hope for is using well, if we replace this G tensor G with a different operator S, then this convolution here is a Cohen's class. So what was my motivation for this was getting concentration estimates for Cohen's class. But on the other hand, if we replace this F tensor F here with a with a different operator t, then what we're sort of hoping for is to see if we can get sort of sufficient conditions for perfect reconstruction of operators. Or I guess if we want to be really quantum, we should consider density operators. So we will see that we can in fact do both of these things. But before we get to the statement itself, I should sort of briefly discuss how we do this. So in the classical case, the large sieve principle is established using a lot of linear analysis. So we're using the short-time Fourier transform, we're using the Gabor space, and we're using modulation spaces. So we're going to need a similar linear structure, which also allows us to use to plug in operators in order to be able to prove this. So the tool we've also seen before today, it's the operator STFT. So most of this we don't need to discuss. Operator STFT is defined as it usually is. Given two Hilbert-Schmidt operators, we define operator STFT as some Hilbert-Schmidt valued function on phase space. And it inherits most of the properties from the classical STFT. There's some Moyal and there's some inversion. But what I want to focus on here again is that the range of the operator STFT, or the range of the Hilbert-Schmidt operators under the operator STFT, is again a reproducing kernel Hilbert space of Hilbert-Schmidt valued functions. And key to the discussion is that the reproducing kernel is this composition of 4 operators. And what we're going to use here is that this allows us to write the identity on the Gabor space as an integral operator with the reproducing kernel as integral kernel. Right? So one last thing we need for the last tool we need is we need, again, since we're interested in local LP estimates, we need to make sure that they're finite. This is no problem in the Hilbert-Schmidt sense, or in the case where p equals 2, but we need something which works for any p. The definition looks quite similar to the definition of modulation spaces for functions, but instead of using the Gaussian, we use the operator, which is the tensor product of the Gaussian. Then we define the operator modulation space as all the operators with a temporal distribution as a kernel, whose operator STFT, where we use this window S0, is a LP function with values in Hilbert-Schmidt. And again, the way we prove this is sort of technical, but the main takeaway is that we get all of the same properties as before. I guess first I should mention that A1 plays a particular role. I will call it the admissible operators, but you could call it the operator analog of Phythian's algebra or something. But similarly, S0 is in A1, but any other admissible operator will also define an equivalent norm on the AP spaces. And again, the inversion formula holds also on the image of AP under the operator STFT. One thing which we'll also need later on is that, of course, we can think of when a rank 1 operator is in AP. And if we fix G to be a L2 function with norm 1, then what it turns out is that the rank 1 operator is in AP if and only if the function f is in NP. So this gives us a nice way to sort of embed the old modulation spaces into these new AP spaces. So with that, I guess we're ready for the quantum large sieve principle. So the quotient we were interested in looks pretty much the same as it does before. We're interested in the quotient of the 2 integrals of the operator STFT. Only difference, of course, is that we have to take the Hilbert-Schmidt norm instead of the absolute value in order to get some numbers. So the estimate is also going to be pretty much the same. We estimate the size of this quotient by the supremum over one variable and the integral over the other of the reproducing kernel. That's the only thing that's sort of surprising here, is that instead of using the Hilbert-Schmidt norm, we have to use the operator norm. And I guess technically, since the Hilbert-Schmidt norm is larger than the operator norm, this would still give you a bound, but it would give you a worse bound. So this is pretty. So in the sense of a large sieve principle, this is pretty much the best bound. So yeah, I guess I'll briefly mention the proof. So the proof uses some, well, it uses basically a bunch of bounding space techniques, but it really boils down to establishing the inequality in the p equals 1 case. For p equals infinity, you have the trivial bound on the L infinity norm, and then the result follows by interpolation argument. And the only thing that's sort of tricky here is that make sure that when you interpolate between A1 and A infinity, you actually get AP. But this is true, and you can show it the same as in the function case. There's some Wiener amalgam space characterization of AP, and then you use the interpolation properties of the Wiener amalgam spaces. So pretty simple recipe, but there's one thing I should say, and that's that what we used here is that we used that we could write the identity as an integral operator with a certain kernel. This works in more generality. So really, if we have an operator that's bounded and boundedly invertible on A1 and A infinity, then we can get a similar bound to this, except where we're integrating the integral kernel of that operator instead. So it will be mostly the same, except that we'll also get a constant which depends on it depends on the norm of the inverse operator. But up to a constant, you'll get the same you'll get the same estimate for any operator which is bounded and bounded invertible. Yeah. So that's the result and the proof. So let's look at some applications. The first, as promised, is Cohen's class. So yeah, we've seen that we can define a Cohen's class distribution by assigning to F the convolution between the rank 1 operator F tends to F and S. And the way this we can use the large sieve to analyze this is by sort of looking at the spectrogram of the operator STFT. So it's operator value, right? So instead of taking absolute value, we have to take the Hilbert-Schmidt norm, but you really get a Cohen's class out of this. So the sort of spectrogram of the operator STFT of a rank 1 operator gives you Cohen's class of SS star of F, at least, and then some powers. So what we really can use, what we really can do here is restate the large sieve principle in terms of Cohen's class. And if we also remember that a rank 1 operator is in AP, if and only if this first term is in MP, we can really restate this as some estimate for F in a modulation space. So yeah, this is just a restatement of the large sieve principle. The right-hand side is pretty much the same as before. Left-hand side is just written out as concentration of the Cohen's class. And so this is quite nice. So even though this is Cohen's class, or not operator valued, right? It's just some function. It's sort of hard to treat the Cohen's class as as a spectrogram, because there's really no like classical reproducing kernel structure on the Cohen class. So we really need to go to the operator valued side to get an estimate which looks like the for the spectrogram. So with this, we can, like before, we can use it to refine an uncertainty principle for Cohen's class. So I guess I won't spend too much time on this, but Franz Lueff and Erling Svela established the uncertainty principle for Cohen's class. That's the same as always. If the energy of the Cohen's class is largely concentrated to some domain omega, then that domain cannot be very small. So they established this using Cauchy-Schwarz, because they were in, well, for one, they were in L2, and for the second part, they had nothing better to do. Now we have something better to do, so we can use the large sieve estimate to extend the Cohen's class uncertainty principle to functions in MP. So proof goes by one application of the large sieve principle. We get that if the energy in the MP sense of a Cohen's class is concentrated to some domain omega, then again that domain omega can't be small. So yeah, not really, and there's not really any more to it, except the fact that I guess you can argue again that this is a refinement, because you get this intermediate term that's coming from the large sieve density. Lastly, as promised, we're going to do reconstruction of operators. And this pretty much boils down to seeing that this Donohoe-Stark type of reconstruction result, it really doesn't matter what the values in the boundary space is. We can just do the same as before. Our scenario is now that we want to reconstruct this operator T, which is admissible via the observations of the operator STFT, where the window is also admissible and has to be normalized. Again, there's an obstruction, there's some noise. The noise, again, it can have finite L1 norm, but we have to assume that noise is concentrated or supported on some domain. By just directly translating this Donohoe and Stark type result, we get a condition for when we can reconstruct the operator T. So if this right-hand side of the large sieve principle is smaller than 1/2, then T is the solution to this minimization problem in A1. And furthermore, it's the only solution. So this procedure of minimizing the norm of this difference in A1 actually really recovers T perfectly. And I guess I should also say that this is a stable result. So if we instead assume that the noise n is almost supported on some domain delta, then we almost recover T using this process here. Yeah, there's not that much time left, but so last thing I'll say is that what we really have here is what this assumption really is some assumption on the really says that this domain delta in some sense has to be small. In some sense, it's a nice assumption theoretically, but due to uncertainty principle and such things, isn't always feasible to find domains which are small and also satisfy the rest of these things. So what we can do in some cases is that if we assume that S is very nice in some sense, then we can replace this smallest condition by a sparsity condition, which in some sense is less restrictive. So if we let, for example, let S be some finite sum of projections of Hermite functions, then we can, instead of using this smallness condition here, use a sparsity condition. So instead of imposing that this reproducing kernel has a small integral over delta, it now has to have small integral when we take the intersection between delta and some disk. So this gives us some sparsity condition which can so easily be checked, at least as long as you know how to compute this lambda star. In this case, it's we know what lambda star is. It's some infimum over a set of the eigenvalues of the localization operator chi. It's the indicator function of delta convolved with S star, which we really know how to. We really know what the eigenvalues look like. So, in some of the cases, we really can replace the sparsity condition by a explicitly verifiable sparsity condition. Yeah, I think I'll stop there. So, thank you for your attention.